Yeah, it's truly my pleasure to come over here and give this talk at your 6G kickoff meeting. So, yeah, so I think we today I think we already heard a great talk from Charlie on the path to 6G. You will see a little bit different views from Qualcomm, but I think the industry is actually pretty well aligned in terms of overall what the pace of 6G and what are the major research areas for 6G. So, yeah, so my talk is wireless innovation for 6G. And before we talk about 6G, it's always good to just take a step back and think a little bit about what the impact we're making for each G, right? So the first transformation that's brought by digital communication is actually this digitized mobile communications. Made actually the mobile phone. Your everyday accessory, you can connect to everyone. And the second major leap is actually we put a supercomputer in your pockets now. So, it's a smartphone that we have. And the third big transformation is what's happening now in 5G timeframe. Is we're connecting not only human beings, but we're connecting all the industry, connecting all the accessories that you want to have. So this is the big picture, and then the question is, for 6G, what we can do. But before I talk about that, also talk a little bit about what we're doing on 5G side. Right? So there are more than 205 operators deployed 5G already, and there are 750 million 5G smartphones already, sold in this year. And there are more than, close to 2,000 5G designs. It's not only phones, right? You have cars, you have CPEs, you have these smart devices. So 5G is really doing great. And we're not stopping because 5G is doing great. I think you have probably seen something like this already. 5G design, in theory, we're done by the end of last year. Now it's called 5G Advanced. So this is the second 5 year of 5G. We're going to have 3 more releases in 3GPP terminology. There will be 3 more releases of 5G Advanced techniques. I'm going to talk a little bit about so you know the background of what's the difference between 5G Advanced and 6G. So, and after that, 6G will start, and the expectation is the 6G standardization will start, according to this chart. The actual specification will start in 2027 or so. The study will start, in 3 years. So this is the 5G. So far, this is everything 5G has covered so far. You can see the release 15, the first release of 5G. We established these foundational designs, including these advanced channel coding, scalable numerology. So you can use the same design for tiny devices and for this, gigahertz of bandwidth, right? Because we had this exponential rule, right? You instead of in 4G you linearly scale, just add one carrier, another carrier, another carrier. In 5G we have exponential rule. It's to the power of n. So you just increase the exponents and you span multiple other magnitudes. So there are a lot of foundational design put into the first release. The second release, we start tackling industry. So the most important ones I want to point out here are, for example, positioning. So before 5G, pretty much we're delivering bits. Even now, when people talk about 6G, I will be talking about it. We're still going to talk about delivering bits, just 10 times more this and 10 times less that. But from release 16, positioning is a completely new use of this cellular waveform. You are actually using this waveform for sensing in the generic sense. So positioning essentially is active sensing. You are sensing the radio. You're sensing object with radio in it. And this morning, I think Joseph talked about the passive sensing. You are sensing objects that doesn't have radio in it, right? So but it started already in 5G. You have sensing already put in there. And then we introduced this cellular V2X, 5G based, have more advanced features compared to LTE. So it's a smart transportation. It is being brought in. And then there are IAB. I think many faculties here did fantastic research on how IAB nodes can work. This is relay, in-band relay, basically, allow you to have very different topology in terms of network deployment. And in release 17, we had more enhancement, but also what's interesting is we introduced something called reducer capability devices. I don't see where it is now. Here. Yeah, it's called RedCap. What this is doing is instead of giving you bigger and bigger and bigger modem, let's handle more, this is actually downgraded to give you something cheaper because you don't need the 10 gigabits per second top and smartphone device type of modem if you want to connect a refrigerator, right? So this is give you the affordability. And release 18, 5G Advanced, is almost a reset. You'll see a few very, I would say 6G-ish topics. So that's where 5G Advanced and 6G actually start blurring. The first one here is full duplex. So that's, many speakers talk about it, and this is a very active research area. My sense is this will be, we'll see some deployment of full duplex base stations in 5G timeframe, but in 6G, this is probably the baseline. It might completely change not only the radio technology, but it also change how spectrum are allocated, right? We used to have pair spectrum, unpaired spectrum. You deploy FDD in pair spectrum, you deploy TDD in unpaired spectrum. With full duplex, what do you mean paired, unpaired? So a lot of things will change. So this will change in my opinion, even the spectrum allocation and how things are going to be allocated. And also you see, machine learning down there, AI machine learning. Machine learning is actually in 3GPP for a while, but most of it is network optimization. You use machine learning for sound, you use machine learning for all kinds of OEM. What's different here is this is machine learning for air interface. So this is, I think many faculties here are looking at. Heiji is looking at coding, right? This end-to-end code, machine learning-based code design. There are also machine learning-based modulation, demodulation, Mimo, precoder, and DMAP. All those things are currently being looked at, and 3GPP specifically will look at three things. One is channel state feedback, another is positioning, and the third one is beam management. So these are, you can see it's a low, I would say hi-fi and low-fi type of air interface design. So 5G Advanced and 6G, they're, I would say 50% overlap, in my opinion. So we'll see how it ends up happening. So the end goal of 5G, what are we trying to achieve? From Qualcomm's view, is we're trying to enable this connected intelligent edge. I would call it the intelligent connected edge because the acronym is cooler, ICE. So, but this is sort of our vision is what 5G is going to allow you to do is to bring the intelligence to the device, and you can also push it back to the edge. Why edge is more scalable, it's lower latency. So why on device is because of privacy, because of reliability and power. But the ultimate goal, in my opinion, what 5G is trying to do is to enable this connected intelligent edge. So then the question is, what is 6G going to do? It sounds, buzzworthy, metaverse, but that's that's actually the reality. Is this is one step ahead of the connected intelligent edge. Is we introduce, everyone talk about digital twins, but from our perspective, there's also a virtual world. What's the difference? Digital world is actually a digitized version of physical world. What's happening here is you are digitizing the physical world and you're controlling it. So you can see sensing going this way and control going back that way, actuators. Virtual world is something that doesn't exist in physical world. Sorry, something. Yeah, virtual world is actually augmenting what you have with something that's that's an augmentation of your experience, right? So this can be really holographic video conference, but it also can be just something very simple, some simple additional labels, even text labels on something. So what 6G is going to do, in our opinion, is to define this interface between this world. We call it the 6G, the new human interface. So that's sort of a step up from what this ICE, the Intelligent Connected Edge. Getting into a little bit more specifics, when Joseph and I, when we designed 5G in Qualcomm, we always ask the question is, what's the supply side, what's the demand side? So without new tools, I don't think we can invent anything significant because people are smart. With existing tools, I think most of the low-hanging fruits have been picked. Actually, the current design is pretty good. Engineers, we never throw out something that works. So there has to be a supply-side change that change the equation. The demand side is there has to be some new requirements, something that's actually a new problem being defined. So we always look at every G transition, we look at what's the supply side and what's the demand side. So on the demand side, I already said the bigger overarching argument is this metaverse. It is a new human interface that's going to connect this virtual world, digital world, physical world. On the supply side are these foundational changes we think is going to change the equation of how we design the wireless system. So some of you probably have seen these slides before. Let me just reiterate. RF change, this is extremely critical. And we know it's advanced RF system are being introduced every day. Sriram was talking about this super adaptive filter based on photonic IC. So that's cool, right? So and they're shrinking the IC by order of magnitude every few years. So if that becomes really feasible commercially, it's going to completely change how we design the filters, how this full duplex, or I think Charlie called it the XDD, this system can work because now you have a truly adaptive filter, right? So this extreme run disaggregation, so O-RAN is already there. Run disaggregation is happening, but from our perspective, this technology will keep evolving, will allow many, many players to come in to build these network elements. And silicon material technology advance, process node is still progressing, so we don't think it's stopping. It's slowing, but it's not stopping. And meta surfaces, meta materials is going to change how we design these antenna systems. So even today, I was forwarded a liquid antenna. People are showing me for race, so it's quite interesting. And then power, energy harvesting, energy storage, many power-related technology is advancing very quickly. This is a huge area I think everyone is looking into. Compute topology, this is what I was talking about in terms of how this computation can be shifted, can be containerized and shifted between cloud, edge, and devices. So this compute technology is advancing. ML, of course, I think Joseph talked about some of the ML work that we're doing, and the whole industry is moving so fast. One of the key things I want to talk to you guys about is 3GPP has a release every 18 months, right? So that's how cellular technology evolves. Is just from spec perspective, it's every year and a half you get an update. But these ML algorithms, machine learning, neural networks, they're not advancing once every year and a half. You look at the benchmarks, every year it's going down very quickly. So potentially with this AI-based air interface, the cellular technology, the 6G technology, will also be actually advancing at the pace of ML innovation. So that's one big change that potentially that will happen, that will shake the industry on how things are actually going to happen. Human interface, XR, and extreme version of XR. People are talking about bioimplants. I'm a little bit scared of that, but these are new technology that's going to have very different requirements, right? This is, for example, linked to what we just talked about, these passive devices. You don't want to implant a battery in your body, do you? So you don't want to rip it out when battery runs out. So yeah, these are all interconnected. And then this is a multimedia display. The biggest problem with AR, in my opinion, augmented reality, I love that technology. I had a demo with my team a couple years ago. Actually, it's very successful. We're running AR glasses, doing these virtual objects, manipulating with our hands over a 5G network. But it's a cooked up demo because we picked a day that's cloudy. That's not, San Diego is famous for sunshine. If you just get into the sun, you cannot see anything. The display technology is not there, right? So if you have both see-through and have high contrast, it's difficult. So I think display technology in the next few years, there are all kinds of trade-offs you can make in terms of how opaque you want it to be. For example, there are display technologies that can handle actually low power and this high contrast, but then you cannot see the person's eyes, which is a no-no for AR glasses if you talk to the people in industry. You want eye contact. You cannot actually shield the eyes. They need to see your eyes. At the same time, in bright sunshine, you need to see the image. So it's very difficult. So these are the sort of the supply side was changing in 6G, right? We're designing a technology for 2030 to 2040. So we believe all this equation will shift because of what's on the left side is going to shift. So with the setup of these new tools, new toys we have, and the new problem we want to solve, so what are the big research tracks? So these are the 6 tracks that we have identified. Of course, machine learning-based end-to-end communication. I think this is pretty obvious. That's going to change some of the designs. When you say obvious, it's not just 1 plus 1 equals 2. Actually, there are specific wireless domain knowledge needed to design this. And there are many things in our wireless communication does not need machine learning. So we can do really, really well without machine learning. If you have very sparse signal that's constructed by human being, actually it's a low-dimensional problem. You don't need machine learning to solve it. So there are many things we can do optimally without machine learning. But there are problems. Well, I'm going to talk about a couple problems that are, in my opinion, that are high-dimensional and we have less understanding on in wireless comm that do need machine learning. The second one is the spectrum expansion and sharing. So terahertz, everyone will be talking about it. And there are not only terahertz, but there are also other frequency range that need to open up. New radio design, there's something called giga-MIMO and full duplex, but also more importantly, new waveform encoding. This is the foundation wireless communications. And there actually, I do see a new generation of coding and modulation and waveform that come up in the 6G timeframe. And merge of worlds I talk about, scalable network architecture. Something interesting here, it's not just a buzzword. I don't know if, is Arun still here? Okay, those hyperscalers are here. And they're already working with operators. And they're also working with Ericsson, Nokia, with traditional infra vendors. They are going to change the equation. So hyperscalers are here. The network architecture is going to change. I think our wireless domain, wireless experts, still what we have a job is how to use them, right? So we're not fighting them, but rather how do we take advantage of the scalable architecture. And the last one is communication resilience. And it may look like afterthought, which is the case in 5G, but it's not for 6G. Because 6G in 2030 is called post-quantum era. So basically, because of quantum communications, our public key exchange algorithm going to expire, right? It is crackable. There are also even this time travel cracking that's happening now. It's can I store your current message? And 10 years from now, because my computational capability is increasing exponentially, I can come back and decode whatever you have. So there are also storage question here. So this communication resilience for 6G is an extremely important topic we have to address. So with that, let me dig into the details. So how much time do I have? Oh, great, thanks. Yeah, coding modulation. All these acronyms, it might look familiar to you, but there are new challenges that's coming. Really, for the waveform side, we need more advanced signal processing to handle higher spectral efficiency, power efficiency, and in different band. This is obvious for different RF frequency. You will need some optimization. But even more than that, I talk about sensing. The waveform that's designed for communication, is it good for sensing? Right? OFDM-based waveform, yeah, some people say it works. Yes, it works. But is it optimal? I don't think so. So there are new requirements that's coming in from the sensing side, right? How is radar designed? Why is radar designed that way? So how do we merge these waveforms? Multiple access, we'll be handling very heterogeneous devices, trying to access the system with very different design functions. For example, if you have a multi-rat, how do we handle multiple set access when you have 5G and 6G mixed together, right? DSS is dynamic spectrum sharing. It's a very successful commercial story, and but that's 4G and 5G. Between 5G and 6G, how do you share? How do you access the system when you have multiple systems that's up and running over there? And then, modulation. A lot of interesting designs these days on modulation side, like probabilistic amplitude shaping. I don't know if any of you are looking into this. Geometric shaping is there, but there are interesting stuff that's happening on the modulation side. I think we do need next iteration of modulation and channel coding. Channel coding is something very close to our heart for many of us, and the NR LDPC code, is really hard to pass the optimality. It's pretty optimal in my opinion, but we do think there are something still that you can do better on the coding side. So I'm going to give you a quick example later. And also this coding modulation waveform, they are not designed in a vacuum. You need to design them in conjunction with the RF change, with the system implementation, right? So for our modem to handle it, the area efficiency we care a lot about. That's directly translated into cost. There are power efficiency and a multi-rat connectivity and different use cases. So really, I think for all the students here and the leading researchers here, coding modulation waveform multiple access, this is our bread and butter for 6G. We will be making use of them, and so this is something I want you to walk away from. So this is just one toy example. These are real curves. I did not just draw them. So x-axis is number of iterations, and y-axis is the required SNR to reach BER of 10 to the minus 6. So this is some earlier LDPC design. I think I'm pretty sure this code is in your phone. And this is the NR design. And so from 2007 to 2017, 10 years, we advanced this curve to the left side by how many iterations for the same SNR, or you can count it both ways. So complexity is reducing to achieve the same performance. The question is for 2027, where are we? So can we actually further lower the complexity for coding? So the walkaway is, not all capacity approaching code are created equal. You can approach capacity in many, many ways, but in reality, they make a huge difference. So this is one slide on Qualcomm's AI and ML research, and also our commercial platform. I think Joseph is leading this effort, right? Both foundational research, this is where we're sitting, wireless. It's just a small part of that applied research. And Joseph is also looking at platform research, quantization, compilation, and other things. So, but today I'm just going to talk a little bit, a small part of this applied research out of our ML research army. Yeah, so I think Joseph already touched upon this. There are strengths on the wireless side, and ML has its own strengths. Maybe one problem I want to emphasize is this hard-to-model problem, right? There are also computational problems, efficiency problems, linearity problems that we're not that optimal yet from communication design perspective. But what I want to say is the hard-to-model problems in communications. I want to give you one example. So like I said, communication signals are designed in a pretty low dimensional space. We can use non-ML algorithm to achieve very good performance already. But there's one part we did not design in the communication system. That part is the channel. So we did not design the channel. And fundamentally, to achieve good communication performance, you will need to have good channel prediction, right? You're just predicting from past to the future. You will need channel compression. This is channel state information feedback, right? So you are compressing the current signal based on the history. Channel inference, this is extrapolation, and the interpolation, you have an observed signal, and some of these, it's okay. Oh, okay. So this is a very advanced formula. I'm trying to hide my ideas. Yeah, but the point is, at the heart of this is this channel model. This is how we have statistical channel models, and we design our whole system based on these channel models. But this is not a real channel. So, so for 6G, part of 5G Advanced as well, we will need to tackle this problem is take a look at the RF environment, and can we understand the channel, and can we generate the channel? So if we can do that in a way that's much better than the statistical channel we have, then our design will also advance with it. Even if the solution we end up having is non-ML solution, just the ML channel itself will reveal a lot more to us. I think that's one area I'm hoping that all the students and faculty here, if you're working on ML, maybe take a look at the channel. That's a part that's very important for overall system design. The second machine learning problem that I want to talk about is the semantic communications. There are a lot of hypes in semantic communications, to be honest. I haven't seen anything that's super groundbreaking yet, but it's a real problem. And when Shannon published information theory, actually, even in 1949, that's what great people do. They write something down, and we're still discussing in 2022. So the information theory is level A communication. It's how accurately you can communicate the symbol that's transmitted, right? We have been doing a great job solving in level A problem. Level B is how precisely the transmitted symbol convey the desired meaning, right? So it's an interpretation of the receiver compared to the intended meaning. This is a semantic problem. And level C communication is effectiveness, how successful you are by conveying the meaning and change the action, get the desired effect out of the communication system. So level A problem that we solved is actually part of the solution for level B and level C. Why this is relevant for 6G? If you think about the interaction between the virtual world and the physical world, we're augmenting our physical world with meaning. So this can be just a multimedia stream, but it can also be simply a meaning, right? So the typical example people use is you send a picture of a rabbit. In the end, you actually only need to know it's a rabbit, right? So level B problem, the semantic problem is actually a more broader sense of virtualization. The metaverse, they add the virtual world. You want to solve that problem. It is a drawing source channel coding problem. If it's only multimedia, yes. But maybe you're also trying to derive meaning. So you have robust communication of this meaning, not just a multimedia stream. And the digital world and physical world is actually a level C communication problem, right? You're not sending bits just for the sake of sending bits. Why do I need a digital twin? Actually, you're trying to use that information to induce an action on the physical world. What you care about is not the bits, but you care about the effect of this communication, right? Let's give you one example is when you send a CQI, you don't care about the CQI, channel quality indicator for those in 3GPP. You care about what throughput you're getting, right? So that's a sort of an easy example. But of course, this is much more broader. So that's a level C communication problem. So hopefully in 6G, we can have more holistic treatment of this semantic communication problem using machine learning. So because these are, in some sense, data-driven problem, as the problem is set up. And ML hopefully can give us also a better solution in this area. Okay, so now finish those two topics. Now let's go down to a little bit more, interesting MIMO, more near-term stuff that we're doing. So there are 3 advanced MIMO techniques, I want to introduce to you today. The first one is full duplex. I think Charlie talked about this, and many of the faculties here are also working on full duplex. What we have been showing actually a couple months ago is a full duplex base station on our top of our headquarters. We're doing full duplex communication on the same 100 megahertz with 2 users that are 800 meters away, 1 TX, 1 RX. So the trick there is we're not doing single frequency full duplex because all the single frequency full duplex system I've seen so far is a small cell type of technology with low power. What we did with sub-band full duplex, what they allow you to do is instead of having TX and RX on top of each other, you put them apart with 0 guard band, you are already getting 45 dB gain because ACLR, ACS, is at least on the infrastructure side is about 45 dB. So immediately they take the full duplex operation from 30 dBm type of range to 75 dBm type of range. Now we have full duplex for macro cells. Now you have low latency, you can have high duty cycle on the uplink, full duty cycle. So in theory, you're going to get like 5x gain in the coverage, but in reality, maybe 3x. So that's a full duplex demo we had. I think in 6G, this is probably going to be the baseline. The second one is something we call GigaMIMO. So this is, we're looking for we used the, we had C-band C-band and millimeter wave drove the 5G deployment and 5G technology design, right? Massive MIMO is underlying technology. For 6G, where is the next order magnitude increase in performance? We're looking at the upper mid-band for coverage. So this is where you have between 7 and 16 gigahertz. And I'm still also looking for a room. That's where the satellite guys also are. But I want to put in a GigaMIMO base station. The definition is pretty loose here. Just the element antenna panel with more than 1K elements instead of 100 elements. So these are, you scale it up, and now all of a sudden this higher frequency can have this very similar coverage as C-band. This enables something called co-site deployment. So for the students here, what that means is operator can roll out their network without acquiring any new sites. They just hang another panel at their cell site. You get nationwide coverage. So it's a more scalable way of deploying a G is to have the co-site property with the previous G. And the third one is a sub-terahertz, and this is a demo system. We showed 100 gigabits per second throughput. It's not going to be a wide area solution for mobile, but it's a pretty good front haul solution and all short range, right? So one use case we're looking at is data centers. So can you replace the wiring between racks with with sub-terahertz? So it's going to change the complexity of data center by a great deal. So these are very interesting MIMO topics, and hopefully you guys are going to look into it. And here are some details in the full duplex. Actually, let me skip it and maybe just point out the design constraints that we have, right? So the key enablers for full duplex is a few part. How do you get rid of the interference from spatial isolation? Our current prototype has 80 dB isolation. The second one is frequency separation. Like I mentioned, in this design, we have 45 dB isolation from there. So right off the bat, I have 125 dB isolation. So that's pretty good to start with. Then you have the beam isolation. I think this is on the order of 10 dB or so. Roughly, that's what you can get. And then you have a digital and analog self-interference cancellation. So there, depending on the implementation, another 10 dB is possible, maybe even more. So this is sort of the set of solutions, but the difference between 5G Advanced and 6G are pretty much this X, Y, Z, how many dB isolation you can achieve. Because like I said, the supply side is changing, the underlying technology is changing. So, for next G, for 2030, I think this capability is just going to increase. So this is the GigaMimo I talked about, why it's possible to go from 3.5 gigahertz to 13 gigahertz. If we keep the same physical size, actually the array size, keep the same aperture, the beamforming gain increased by order of magnitude, which completely offset the propagation loss. You still have penetration loss to work with, but that's manageable. And also at this higher frequency, you have higher resolution in terms of positioning and sensing. So this is a really promising technology. We think this is, if we do it right, we can have the best of millimeter wave and best of sub-6 in terms of bandwidth and coverage. If we don't do it right, we get the worst of sub-6 and the worst of millimeter wave. So this is a tough engineering design problem, and we are Qualcomm. We are making the prototype right now, and in a couple of years, 2024, hopefully I can show you a live system. It's going to cost me a couple $1 million for that one base station. Hopefully the likes of Ericsson can, make it, Ericsson, Nokia, you get to make it, 100K instead. So, all right, so last one is on the topology evolution. So far I've been talking pretty much about physical layer, but the network topology is evolving. From 4G, where you have eMBB and massive IoT, to 5G, you're enabling more services, to 6G, when we have this converged world concept. The network topology is also changing, right? You have regional cloud to edge cloud to cell side, actually on-prem cloud. So network topology is changing, and this is, when we design the 6G system, we also need to take that into account. So, all right, so the rest two slides are summaries of what we did on 5G Advanced in terms of prototyping. On the foundational air interface side, we demonstrated advanced Mimo, millimeter wave. This is actually AI-based air interface. Earlier, we demonstrated this end-to-end with our AI100 network side neural processor and our Hexagon on-device neural processor. We actually replaced the CSF of a 5G system, used machine learning. So it's running actually on release 15, commercial base station, commercial handset with this change, and the prototype base station we have. So, and then we have green networks. We have 16K QAM without increasing actually the RF requirement. So the trick we did is we did a lot of receiver processing. So we relaxed all the TX and let the signal distort it to hell, but on the receiver side, we recovered it. So some green technology over there, and some positioning evolution. The other side are the new services and applications that we demonstrated. A lot of interesting stuff over there. This advanced automotive safety, here we also solve, we augmented the auto system with additional information from 5G. And also we had radar interference mitigation. These are Shailesh sitting in the audience. And if you have any questions on these auto-related questions, you can ask Shailesh, sitting over there. So with that, we finished the talk with, this is the Qualcomm propaganda. We have, you can see this is how pandemic changed how we interact. For everything we want to say, we make a YouTube video and just chat about it. But I think it's in the deck. If Jeff, if you distribute, I think you have the link to each of them. And we have a playlist. You can go through these 20-some demos that, that we have. Okay, thank you very much. Yeah.